Hello everyone, we are Team C242PS30 and we are excited to present Tech Sehat today. Before we begin, allow me to introduce my captain team. I am Nazo Sophia and Fatia Jasmine, part of Cloud Computing team. From the machine learning team, we have Rafael Hanley, Hieronymus William, and Federico. On the mobile development side, we have Alvi Husna and Sally Hairunisa. Together, we combine our skill to bring Tech Sehat to life. I will begin by background of Czechstat. Healthcare accessibility face challenges like long waiting time, high costs, and limited facilities. This project aims to develop a chatbot for symptom screening and initial health consultation. Integrated with a database of health articles, the chatbot will provide quicker access to health advice and relevant information, bridging the gap between patient and healthcare providers. Next is the reason for Check Sehat. We chose this theme because many people are affected by diseases without understanding their causes or symptoms. The problem we aim to tackle is the lack of awareness about how certain activities can lead to illness. With Check Sehat, we want to help users understand the cause of diseases, recognize their symptoms, and learn how to manage and prevent them. Check Sehat also provides health articles to give users relevant information, empowering them to make informed decisions and take better care of their health.
In this section, I will present a comparison of existing results between Halodoc and CheckSehat based on 5 main aspects. 1. Purpose. Halodoc focuses on telemedicine services that provide remote consultation with doctors. Meanwhile, CheckSehat is designed as chatbot to screen symptoms and provide health education. 2. Health education. Halodoc limits education to the consultation context only. In contrast, CheckSehat provides health articles that aim to help users with prevention and treatment. 3. User interaction. Halodoc does not have ongoing user health tracking features. On the other hand, CheckSehat allows users to track their symptoms and health history, providing a more targeted and supportive experience. TechSehat comes with innovative features to help you maintain your health. 1. Chatbot feature. With our chatbot feature, users can easily find out the causes, symptoms, and how to prevent various diseases by simply typing in the questions. 2. Health article features. We also provide relevant and reliable health articles from credible sources. Users can increase their knowledge about health through this feature.
Now I'm going to talk about our target market of our capstone project. Our target market includes individuals aged 18 to 65 years old, particularly those proactive about managing their health. We also focus on busy workers, family caregivers, and individual prioritizing personal well-being. And additionally, we target tech-savvy users who value fast, reliable, and convenient health solutions. Now I'm going to tell a few of our SWOT capstone project. For the strength, we got accessibility that is available anytime, anywhere with an internet connection. And for the weakness, we got limitation that the model struggles to explain complex disease accurately. And then for the opportunities, we got high market demand that more people are searching for health information online, presenting a great opportunity to engage users. And for the threats, we got disease evolution, that change and evolution in disease can make the information provided by the chatbot less relevant now. And yeah, right now I'm going to explain about how machine learning works for the implementation of the chatbot. First, we find the dataset by searching the dataset on Kaggle, cleaning it, and pre-processing it to remove the unwanted characters and tokenize the word. Quality of the data is very crucial for the model performance. Next, we build the model architecture. We use an LSTM network for the mental health chatbot, which handles sequential data very well, and pre-trained GPT-2 model for the general disease chatbot, which is very powerful and can be fine-tuned to our dataset. Then we train the model. For the LSTM, the model uses text sequence to learn the pattern and context, and for the GPT-2, the model fine-tunes the pre-trained model to our dataset. Training involves adjusting hyperparameters to optimize performance. Once trained, the model can predict text-based answer with input prompts, provide seed text, and the model will generate the answer. Finally, export the model to saved answer and deploy it on application. The performance of the LSTM network for the mental health chatbot is very impressive, with an accuracy exceeding 94% and a loss of 17%. This high accuracy indicates that the model effectively learns and predicts patterns, providing reliable and accurate response. Although there is a room for improvement in the loss value, the overall performance demonstrates that the model robustness and utility in offering mental health support, highlighting the potential of AI in this sensitive and impactful area.
Let's first talk about the LSTM model that we created first, and then we're going to talk about the model that is using pre-trained model. Let's start with the accuracy over epoch plot on the top left of the LSTM model. The blue line represents training accuracy steadily increasing, while the orange line shows the validation accuracy following a similar trend. This indicates the model is learning effectively and generalizing really well. In the loss over epoch graph below, both training and validation loss consistently decrease, further confirming that the model improvement during training. Moving to the model summary, the LSTM layers are crucial for handling sequential data, but they have limitations. LSTM models struggle with long-range dependency, especially in large dataset. Despite the promising metrics, the chatbot's responses are often irrelevant and lack of coherence due to its limitation. Let's first, on the GPT-2 side, the training versus evaluation loss graph shows steady improvement with the evaluation loss stabilizing, indicating strong generalization. The ROC F1 measures graph demonstrates a high score exceeding 64%, reflecting coherent and relevant chatbot responses. The GPT-2 model summary reveals its robust architecture, with 12 transformer blocks and over 124 million parameters, enabling nuanced text generation. The training loss dropped below 1.50, and the ROC score indicates that the model is well suited for health-related inquiries. In summary, while GPT-2 excels in coherence and relevance, the LSTM model, despite good metrics, struggles with response quality due to its inherent limitations.
We developed a RESTful API to support the backend machine learning models by utilizing two popular frameworks, namely Node.js with Express and Fast. In this project, Express is used to handle the communication between the front-end application, such as a mobile app, and the backend, including receiving requests from users and sending relevant data to the machine learning model. Meanwhile, the Fast framework also allows the deployment of machine learning models in a structured manner, making integration with other systems simpler. Next, I will explain the code architecture for this project. All interactions start with user accessing the application through their device. Firebase authentication verifies the user's identity to ensure secure. After login, CloudRun processes each request by executing backend logic. Important data, such as user data, interaction history, or articles, will be managed by Firestore, while files such as ML models or documents are stored in cold storage. Artifact registry supports this infrastructure by storing application container image to ensure stability and easy of deployment on CloudRun. Next, for deployment, we use CloudRun to run our chatbot. The chatbot consists of several parts that we have packaged in containers or Docker image. These containers are stored in the artifact registry and then run in CloudRun. Once deployed, we can access the chatbot through the web address or URL provided by CloudRun.
Next, development article. I developed a backend API for article using FS Code to manage and provide article data for the app. After development, the API was connected to the cloud, deployed using Cloud Run for automatic and scalable operation. The article data is stored in Firestore, an OSPL database for Google Cloud. This setup ensures quick, secure, and efficient access to article data whenever needed. Next, we have 7 endpoint, which you can see on the screen.
In this project, we use several tools and patterns to ensure smooth app development. First, we designed the UI/UX using Figma, which allow us to create the app interface. After completing the design, we move on to the integrated development environment, specifically Android Studio, where we translate the design into code. We also implement Firebase for user authentication, ensuring that users can securely log in and register. To structure our app, we adopt the FVVM model view model pattern, which help us separate business logic from the user interface, making the code base more maintainable and organized.
Moving on to the implementation slide, we started by creating the UI/UX based on the Figma design. The design were then laid out using Kotlin in the XML format to bring them to life on the app's interface. We integrated architecture components such as view model and live data to efficiently manage the data that is displayed on the screen. For API integration, we utilize retrofit to perform API calls, allowing us to fetch and display data from the server smoothly. Additionally, we perform thorough testing to ensure that the app is functioning correctly. Now that we've covered the development process and the technical aspect, it's time to show you the results. We will present a mock-up of the Cek Sehat app, followed by a demo video that showcases the app in action.